This is a mixed review where we compare two different test methods for the same data set just to see the similarity and differences. So we're looking at gender, male and female. Just to note, if there were more types of genders, I could easily add them to this table and I should be able to still do similar analysis. And I have they either go on the ride, high tide, or they do not go on the ride, high tide. And I want to test if there's a relationship between gender and ride preference. So the data that I'm getting here is either ride or not ride, male or not male. So each of these things feels like a category. I am looking at categorical data here, or another name for that is qualitative. So I'm going to show you the two different ways of sort of analyzing categorical data using a test. I want to do just a little bit of scratch work. I'm going to try to figure out as much as I can with this table before I do anything. So first thing I'm going to do is I'm just going to add everything up to see what my totals look like. I feel like that might help me out. 250 plus 390. There were 640 people that went on the ride. 640 and 720. There were 1,360 that did not. This gives me an overall total of 2,000 individuals. For the individuals that she sampled, 890 identified as male and 1,110 identified as female. A little bit more scratch work. I'm just curious what I'm looking at. Let's try to figure out the proportion of males that went on the ride and did not go on the ride, and the number of males. Let's figure out the same thing for females. And I also want to know what my overall success rate looks like, and by extension, what my overall failure rate looks like. So for the male group, I had 250 went on the ride out of 890. For the amount that did not go on the ride, 640 out of the 890 did not. So I'm just taking success over number of trial, failure over number of trials. And the number of trials that I'm looking at are 890. For female, I have 390 out of 1,110 for successes. For failures, I have 720 out of 1,110. And for number of trials, 1,110. So I have these values that I'm working with. I can change those to decimals. If you're more comfortable with decimals, do that. For my overall success rate, I had 640 out of 2,000 went on the ride. This looks like this is a pretty nice decimal, so I'm actually going to type this into my calculator. 640 divided by 2,000 gives me 0.32 or so. And this tells me if 32 went on the ride, then 68% did not go on the ride. Whew. Okay, so just some prep work. I have success rates and failure rates for the two genders that were observed for this particular sample. And I have my overall success rate and my overall failure rate. I'm going to do a hypothesis test, which has the same 4 steps every time: null and alternative hypothesis, model, p-value, and conclusion. The two ways I have of analyzing this categorical data with multiple variables is I could do something called a 2-proportion Z-test, or my other way of looking at this is going to be using the chi-squared model. Let's start by doing the 2-proportion Z-test. The null hypothesis there will be that the proportion of male riders is equal to the proportion of female riders. In other words, that there's no difference between the groups. I'm testing for a relationship. These numbers will be different if I have some sort of relationship between the variables. Ultimately, this is the same thing that I'm testing when I'm doing chi-squared. I wonder if I have the same distribution, success and failure, for both male and female. I'm going to write down the null and alternative hypothesis the same way on each of these. Usually I write down the null and alternative in words when I'm working with a chi-squared test of independence, but that's okay. The null hypothesis would represent that it is independent, that there's no relationship. The alternative would be that it's not independent, that there is a relationship. So that's how I usually write it. Okay, we're going to do the 2-prop z-test first. My model for this, I'm going to be comparing male minus female. It will follow a normal distribution. The center will be 0. When I do a 2-proportion z-test, I have to pool. And I'm going to take my pooled success rate times my pooled failure rate over number of samples for the first group, pooled success rate, pooled failure rate over the number of samples for the second group. The reason why I'm pooling is in the null hypothesis, I'm assuming the 2 groups look the same. If they look the same, I'm just treating this as one overall success rate, regardless of gender. So my model, no difference is the null hypothesis. 32% success rate, 68% failure rate. Number of samples in the first group was 890. 32, 68. Number of samples in the second group was 1,110. I'm going to type this into my calculator, and I'll see what I get for my standard deviation. So I have square root 0.32 times 0.68 over 890, 0.32 times 0.68 over 1,110. I'm not going crazy with my parentheses here. Order of operations does a lot of it for me. This gives me 0.021 if I round a little bit. So my p-value, this is going to be the likelihood of having my success rate or more extreme, whatever symbol I have from the alternative. And this is where I will compare my actual success rates for the group. So for male, I had 250 out of 890. And for female, I had 390 out of 1,110. I'm going to type this into my calculator to see what I get for my value. My value that I still have to put on my curve and find my z-score and find my p-value using. But I currently have a difference of 0.0705 or so. So on my curve, I have zeros in the center, and I am counting by 0.02 or so. I had a difference of negative 0.0705, and I want that or more extreme. In this case, I'm testing for a difference, so I'm going to have a 2-tailed test. So I'm going to find my z-score. I'm going to look this z-score up in a table, and then because it's a 2-tailed test, my p-value is going to be 2 times the value that I get from a table. To find a z-score, I take my value from my data. So I have my data value minus the center 0, and I divide this by the standard deviation, 0.021. So again, I have my value minus my center over my standard deviation. This is how I find a z-score. When I do this, minusing 0, I don't even have to worry about that. So I didn't even type in -0 on my calculator. I get negative 3.36 or so. I can look this up using technology, so I can go in GeoGebra and type in the z-score. I work old school sometimes, and I still go back to these normal tables because I find it gives me a little bit of number sense. I'm looking up negative 3.36. When you're using these tables, you have your first digits of your z-score, so negative 3.3, I'm in this row. Last digit was 6, I'm in this column. And I see where they meet up, 0.0004. This is the size of this left tail. I have 2 of these tails, so when I multiply this by 2, I get a p-value of 0.0008 or so. If I use an alpha level of 5%, this p-value is smaller than that. If the p-value is low, the null must go, so I would reject the null hypothesis. If I reject the null hypothesis, this is telling me I have evidence of the alternative, so I have evidence that there is a relationship between gender and riding high tide. Hypothesis test conclusions always seem like a bit of a bummer to me because this is telling me that there is a relationship, but it's not telling me what that relationship actually is. And to me, that second question is far more interesting. That's what a confidence interval does. So if you're wondering how this data is actually different, I would strongly encourage going and following this thing up with a 2 proportion z interval. In general, confidence intervals are a bit more descriptive than just the test. But I do have evidence of a difference. So this process again, hypotheses, my model, I had to pool when I did the model, that's okay. I found my z-score, I looked the z-score up, it's a 2-tailed test, and I had evidence of a difference here. Let's see the same thing now as chi-squared. Reminder of how chi-squared works. This looks at the sum, this means add or sum, of the values that I observed minus what I expect squared divided by the expected. It has a degree of freedom of the number of rows minus 1 times the number of columns minus 1. We'll see why that's the case. And it has expected values of the total of the row times the total of the column divided by the overall total. So let's use this information for our data set here. So we already have a table of information. This is what we observed. I need to make a similar table for what I was expecting. So I'm going to have the same totals, and they either ride or do not ride. My total still 640, still 1360. I have the 890, the 1110, and the 2000. By preserving the totals, when I'm finding this expected value, I'm technically pooling my data together when I'm finding out what it looks like to be fair. So my expected grid here, this is equivalent to pooling. I still see this 32% success rate and the 68% success rate living inside of it. Now, if I have a 2x2 grid, my degree of freedom will end up being 2 minus 1 times 2 minus 1, 2 rows minus 1, 2 minus 1, 2 columns minus 1, 2 minus 1. This gives me 1 times 1, or just 1 for my degree of freedom, which means I only have to calculate one of these expected values using this multiplication trick, and then I can find the rest using addition and subtraction. So let's find this one. Expected will be equal to the row this lives in is 890. The column this lives in is 640. And this has an overall total of 2,000. 890 times 640 divided by 2,000. I have 284.8. It's okay to have a decimal. To figure out this value here, I could do 890 minus 284.8. So this is 605.2. I have going down 640 minus 284.8. So this would have to be 355.2. I'm just making sure that everything adds up now. Last value should work both vertically and horizontally. I'll do horizontally because the numbers are a little bit nicer. But I can verify this vertically by taking this 754.8 plus 605.2, and I should get 1,360. I do. So you'll notice that as soon as I have this one grid, I could solve for the remaining ones. This is why the degree of freedom there was 1. So I solved for one of the expected values, and then I got the rest for free. That's pretty nice. I'm going to calculate my chi-squared by taking the observed value, for example, 250, minus the same thing but with the expected, 284.8, squared divided by the expected 284.8, and I'm going to add this up for each of these values. Now, as I go through, I typically cross them out to make sure I don't miss any. So I've already done the 250 paired up with the 284.8 number. I'm going to type all these into my calculator. So I have 250. This got paired up with this 284 number. This got paired up with that 284 number. The 640 is getting paired up with the 605.2 divided by the expected. My next number is 390. That got paired up with the 355.2. And the last value was 720 minus 754.8. This was paired up with 754.8. This gives me a chi-squared value of 11.27 or so. Chi-squared will always end up being a right-tailed test. The reason for this is I've squared everything. A positive squared stays positive. This negative, when I square it, will become positive as well. So my picture for this thing is going to be a right-tailed test. My chi-squared is 11.27 or more. It's going to be shaded like this. My p-value, I'm going to do chi-squared CDF from 11.27 to infinity. It's a right-tailed test. So I always have my chi-squared, infinity, and then my degree of freedom. My degree of freedom here was 1. I'm going to type this into my calculator, and I can use second vars on my TI-84 to find chi-squared CDF. If I'm in a TI-89, I would do apps, stat list editor, and then F5 to pull up distribution. If I'm doing this inside of GeoGebra, I'm going to open up probability, and I'm going to use the chi-squared model. I have 11.27 to infinity, degree of freedom of 1, and this gives me a really small p-value of, and if I round this thing, this is closer to the 8 than it is to the 7. So let's see, that's 0.1230, and then an 8 if I round this thing correctly. This is a really small p-value, if my p-value is low, then the null must go. I would reject the null hypothesis. If I'm rejecting the null hypothesis, this means I have evidence that they're not independent. I have evidence that there is a relationship. This is exactly the same conclusion I got before when I did this using this two-proportion z-test. So looking at the two things side by side, let's see how they compare. Well, first observation, p-value of 0.0008, p-value of 0.008. So no matter how I cut this, I'm going to have the same p-value for both my chi-squared and my two-proportion z-test. It's the same data and it's the same hypotheses. It should stand to reason that I have the same p-value as well. Second observation, I had a z of negative 3.36. I had a chi-squared of 11.27. But if I'm looking at the chi-squared process, I have squared all these values when I'm combining them. So just out of curiosity, I'm going to see what happens if I take this negative 3.36 and I square it. Well, that gives me 11.27-ish. So when I take my z-score and I square it, this should give me the same value as my chi-squared, up to a little bit of round off there. So this tells me I now have a way of essentially double checking my work with either one of these processes. So if I'm better with chi-squared, I find that I'm a lot better with chi-squared. I don't have as many nasty square roots to work with here. I can double check this using this z-score squared to see if I'm on track or not. So this was the process for going through using both a two-proportion z-test and chi-squared. I had the relationship z-squared equals chi-squared. Likewise, when I did the same thing for quantitative data, I ended up having the relationship that t-squared was equal to f. So this tells me that in a lot of ways, chi-squared and z are really similar models, and t and f work very similarly as well. So you have options when it comes to your statistical analysis.